So you're seeing my screen, right?
Yes, we see your screen.
Okay, and here as well. All right, hi everybody. Good morning. I'm excited to be back with you guys. And today we're going to continue our discussion on interpolation. And my goal is that we can actually go through and finish this interpolation script. And I think it's going to be a great resource because anytime that you need to do interpolation for your things out and about, you can always use this script as a resource for you to, as a basis, and then build from there. So that's kind of, it's been kind of my goal, is to show you things, but also to, at the end, you're going to have this resource that you can use after the course. Okay, so, to get started, I always like to start from the beginning. So I'm just showing you here, we're going to be using RStudio today as well. And I'm just showing you here my overall course folder, right? And so the one where I have the RStudio project icon that I want to go to is the one with my initials. So I'm going in there. I see that code, data, and output folders. I also see this .rproj icon. That's what I want to double click to launch my RStudio environment. And again, I know that, like, I think most of you guys have been able to get this workflow of like using projects and having that folder structure and all that. If you have not, please let me know, because I think this is a very important point of not getting stuck on things, because the project again sets your directories, and so when you're importing or exporting data from into and out of R, it's important to have this in place. Okay, so once you double click that R project icon, is going to launch your RStudio for this project, and you know that because you should see the name of the folder. So in your case would be your initials at the end, where this project is on the top. If it says project none, it means you did not properly open this project. You have issues. You're going to have issues most likely importing and exporting data. I assume that all of you guys have been able to see your project name up there, just because we've been doing this. But if you haven't, let me know and we can always stop and troubleshoot. Okay, so once you have your project open, you come on the Files tab. You can click on that R blue button there to take you to the home directory of this project. And what I want to ask you to do is, if you're not yet seeing your partial script up here, if it's not there, I'm going to close mine just to simulate that. If you're seeing something like this, you'll come on the Files tab, click on that R button to take you to the root directory, go on code. And I have a few more things here that you don't have, but you would click on your interpolation partial to bring up that script up here. When that happens, you can minimize your console if you want by clicking that button right here. That gives you more space to see your actual R Markdown script. Okay, so we're gonna have to slowly, or initially slowly, rerun what we had from last time that we met, just so we can get to the point that we stopped last class. So if you want to go ahead and run this first chunk here, which is basically just loading all the packages that we need for this exercise, you can run then and if you have any issues at any point here, please let me know. I don't anticipate too many issues because we've been through this already, but if you have, let me know and we can stop and talk about it. So once you ran that first chunk, you can run the second chunk here to import the yield 17 cleaned data. So just as a reminder, this is the data set for the field. So that the field that we were using, we had yield data for 3 years, 2017, 2019, 2020, if I'm not mistaken. And we're going to go through the interpolation of the 2017 one today. And on the clean version of that. So previously to the interpolation, we were doing the cleaning part that you guys all did through the assignments. This is the actual version that we're using today, is that clean version. And this code should be there, but if it's not, just make sure that you're importing the clean version that either you produced or I share with you. It's being imported because if you run the chunk and it prints here, the output, it means that that object exists and was printed. You can also see it on the environment on the right. So here, the summary is not really creating anything. If you want to run it just to check, I'm not going to spend too much time here because we already covered this. And then the next step would be to import the boundary. And here's a really important point that I want to make about perhaps a mistake that I made, and mistakes in programming are super common, right? We learn from them. But last time, I don't know if you recall, the last thing we did was to create a map where we showed the yield points in the grid that we created. And initially, I was having issues with my own code here, and you were, because you were following me, that the map was not showing properly, right? It was like distorted. It was not what we thought it would be. We could not see the yield data. And that was because initially, last class, I had not included the ST transform here, meaning that we read the boundary and it was in WGS 84, so geographic in degrees, geographic reference system in degrees. And when we plotted that with the yield, which was NAD ETM NAD 83, which is projected, it's in meters, and we plotted both of those, so a meter and a degree layered together, they got all messed up and the plot didn't really show anything. So just wanted to make sure that you last class did come back on this chunk and included that transformation, which basically takes the boundary that initially is in degrees, WGS 84, and transforms that into UTM, which is the same as the yield. We want them to be the same. And again, here we're doing interpolation. So we're working with distances, we're working with that measurement of distance. It is important that's in meters, or maybe feet, if that's also an option, but we're not using feet here, we're using meters, but it's important that it's not degrees, because degrees change depending where you are in the globe. Okay, so if you just want to run that boundary, you should see what I'm seeing here. If you come here on the first panel, you should see that the projected CRS is NAD 83. So this should be true for your case as well. Okay, so you should already have this code here. It was basically just a map where we're basically, you can just go ahead and run it, but we're basically showing the yield data with the boundary, right? So basically the two layers that we imported, we're just now plotting them to see them. So we see that it is the clean yield data. We see some gaps from the data points that we removed. We also see the boundary around it. And we're going to use the boundary as the frame to create a grid. And it's important to create the grid because the grid is what we're going to interpolate on. So the grid is going to look at whatever values of yield is below it and use that to interpolate on the grid cell that we define.
So I want to interrupt here just to tell you a little bit of a funny story related to the map you're showing us. So a few years ago, we had a colleague here. I won't say his name, but it was when we were first delving into yield maps, creating the very first yield maps for southeastern crops. And of course, the edges of the field were always showing lower yields, and we went to a farmer's meeting where we were describing these yield maps, and he said, we just really need to get rid of the edges of the field. And this is what you've effectively done here, Leo. So this is great. Our colleague would be very proud.
Yeah, and just, that's a great reminder as well that because this is the clean version, if you guys remember, one of the filters we did was using this same boundary, creating a negative buffer and removing points that were overlapping in that negative buffer. So that's basically doing what you're describing, George. Yep. Yeah. All right, so we talked a little bit about different interpolation methods, and we're going to be using inverse distance weight. I'm not going to get too much into details of that. And we also, if you come to the next chunk here, we had last class already created a grid, and this grid is in a vector format. So the only thing to really note here is we're using this function to create a grid based on the boundary. And we ask for the cell size to be 10. And in this case, 10 what? Well, 10 whatever units boundary is in. Boundary is in meters, and so it is 10 meters. If we had not changed boundary, if we had not transformed boundary to UTM, meaning meters, if we're still in degrees in WGS 84, 10 here would mean 10 degrees. So just so you're aware, this is a numerical number, but that goes back to whatever unit that layer is in when you use the grid function. And I have a V here just because I wanted to say that that's the vector version of this of this grid. So if you just run that, I mean, it prints, the way it prints is a little bit different because now we have polygons and we really don't have any other data attached to this grid at this point. So it's just showing some information there about it. And just again, making sure it's NED 83 UTM zone 16 north, which is where this field is located. And then I believe we stopped here. Is that right? Do you guys have this code here on this chunk? Okay, I think that's where we stopped. And so I'm just gonna run that if you want to go ahead and run that as well. So what is going on right here is we just now overlay the grid on top of the map that we had created previously. And one thing to note is at this point, this grid is a vector, pretty much meaning that each one of the cells is like a small polygon. And I want to tell you here that and this is kind of like, it depends on the function that we're using. The function that we're going to use next to do interpolation requires a raster grid, which we don't have yet. We have a vector grid, and it requires a raster grid. And we're going to do that transformation, transform this grid from vector to raster pretty much to be able to do that. And before we do that, I just want to quickly show you here. I know that maybe some of you already have a pretty good grasp on what is vector, what is raster, what's the difference, but I just want to quickly show you an example that I think it helps in case you're wondering. Let me just go back. It's actually this one here. So this here is one of the books that I have on the resources, and they have one chapter that I think explains this kind of nicely. So if you look here on this plot, they're just showing this interchangeability between vector and raster and how does that work. So if you look here in our on this 8 points panel here, this is a point. You can see the points, right? It's a point shapefile, and maybe I shouldn't say shapefile. It's a point vector because shapefile is the way that Esri refers to vector files, but it is a point vector. And vectors can be point, can be polygon, can be lines, as we already saw some of those. So for example, our boundary is also a vector. It's a polygon vector in that sense. And then here is just showing that if you were to transform this point shape file into a raster, this is what it will look like. It would basically, you have to define a grid size, which you kind of see here, the size of the cells that they defined for doing this transformation. And then every grid, every cell of that raster that there is a point equivalent to it, it just basically assigns a value to it to say that there was something there. So this is like the yes, no transformation on a raster format from this vector file. And just so we have some other example here. So let's say, looking here at this line rasterization. So what if you have a vector and you want to go to raster, which is what we're going to do next. In this case here, you can kind of see this black line around it. Imagine that you have that black line and you want to, and again, a line is a vector, but what if you wanted to transform that into a raster? You would basically, you have this grid cell, and here we see the centroids of the cells. Wherever that line touches a grid cell in a raster format, that's where that pixel would light up. So like going around it, or in the case on the right here, it would be a polygon, it would be whatever the boundary and what's inside of it as well. So just to show you some differences here. And also, I think perhaps the one that to me makes a lot of sense is just looking at Google Maps, for example. So if we were to, let me zoom in here. So given what I told you guys, maybe it wasn't as clear yet, but can anybody guess if what we're seeing here is vector or raster?
Raster.
You think it's raster? Why do you think that?
I think it's vector.
I guess because when you zoom in, it'd be pixelated, but I guess at where it is right now, it could be a vector.
Yeah, and that's a great conversation to have, because actually what we're seeing now is vector. So notice how like we don't see the grass actually, we see like a polygon representing the field, we see polygons representing things. And a vector file, you can zoom in indefinitely. You will never break the pixel because it doesn't have pixels, right? However, what about now?
There's the raster.
That's the raster. Yes. So this is the raster, right? So this is just so you see this like difference of what is raster, what is vector. And really, if you think of it, the way that Google or whoever else did it the way that they did to come up with the vector file is they started with the raster, right? So it's a satellite taking imagery of the entire globe. And then they basically have algorithms that go into that imagery and say, this part of the field here is grass. Let's just combine all that into one polygon. And just basically pretty much does that for all features in that satellite imagery, just classifying those pixels into objects that then become vector. So I know that when I was learning this concept was a little bit confusing for me, like what's the difference? And I hope I was able to at least give you guys some idea of that difference. So just coming back now to our exercise here, the whole idea of talking about that is because right now our grid is in the vector format. And we know that because if we ask for a class, it is an SFC, which means it's coming from the SF package, but it's a polygon. And if it is a raster, it is not going to be polygons. It's going to be grids with, it's going to be a grid with raster cells, where each one of those raster cells is going to have a value. And right now, that's not what we have. We have polygons. So let's just come here to the next chunk here, where we're actually going to transform our grid from vector to raster, because that's what we need to do the interpolation. See my cheat sheet here. Okay. So we were basically, if you come here to that part of the code, we're going to use the assign symbol, and we're going to start with our grid underscore vector object. And then you can go ahead and include a pipe there. So we're going to be using the pipe in this workflow here in a few lines of code. And we're going to use this function called st underscore s underscore sf, which is basically making sure again that this vector layer is in an SF format. And then after that, we add another pipe, we hit enter, and there is this function called st underscore rasterize. So this function is basically rasterizing a vector layer, which is kind of what I was showing you guys earlier on that book down, where we have the line and the pixels lighting up behind the line, creating that raster file. So there are a couple arguments inside of this rasterize function that I want you to add. One of them is dx. So dx is basically just a dimension that you want to change in the x scale. We want that to be the same as what we created. So it's going to be equals 10. You can add a comma and type dy, so the same thing, and add 10 as well. So basically using that vector grid and just reassuring again that when we go to raster, we want to keep that dimension that we initially set up. And then lastly, I want you to add a pipe there. So when we do this, it's going to basically, this up until this point is going to look exactly as what we're seeing up here, but on a raster file instead of vector. What I want to do in the next step on that pipe flow is to basically clip now this raster to only the boundary. So because we really don't want to interpolate outside the field boundaries here. It doesn't really make that much sense. So to do that, we come here back to this chunk, hit enter, and then there is a function called st underscore crop that's cropping this entire raster only to our field boundaries. And then we just have to say boundary underscore W, because that's the object that we want to crop based on. So if you go ahead and run this, it should have appeared on your environment. If you just print it, now it's a little bit of a different object. So it looks perhaps initially similar, like you have two panels when you print it, but when you go come on the second one here, it does not look at all as what the vector used to be. And I just want to tell a quick history about our geospatial packages. So in the past, there was a package called Raster, which is what people use to do any type of raster manipulation, really. And that package is being, I don't think it's being updated as much anymore, and it's being replaced sort of by another package from a different person that actually fits better with the tidyverse scheme of things, of like using pipe and having some of that same philosophy behind it. And that package is the package called stars. So this is a stars object. If you do class, you see that it is stars. Basically, that stars name means that it is a raster file that is being created and manipulated through the stars package, really. Okay,
So a minute, please, because I have an error, and I have an error with the st_as sf function. Does anybody else have an error? No.
Well, could you tell me?
Oh, okay.
What is
Never mind. I found a typo. I just wanted to make sure that I saw what you were doing there.
Could you share with us what was it?
Oh, it's okay. I have a typo. I found it.
Awesome. And also something that I think it's a good moment to perhaps mention that if you have a pipe flow like this and you run the entire thing and you get an issue somewhere, you can always add like a comment off right before a given pipe and run this, which basically is going to run up until here. And then that way you can kind of make your way up, or maybe make your way down and really find where specifically in that pipe you're having issues. That's a good tip for troubleshooting as well. Okay, so let's plot this. Let's see what's going on here. So I basically want to call again that yield clean underscore map object. That is a map that we created and saved to this object. Add a plus, and then we're going to use a geom underscore stars. So notice how before for vector we were using geom underscore sf. Now we're using geom underscore stars because it is a raster file being created through the stars package. So we're just going to say data equals grid underscore r, which is what we just created above, transform that vector to raster, add a comma, and I just want to say alpha equals 0.7, just so we give it some transparency so we can see through it what's behind that layer. So if you run it, you should be seeing something like this, which now is really interesting. It looks different. Like, it does not look like the grid we had before. And the reason for that is this grid now it still has, like, if you think of it, the bounding box is still the same as the vector, but we cropped it to only contain the boundary. So what it did is now we have pixels because it is a raster file. For every pixel that's outside of our boundary, it has, I think it's a 0 value, or perhaps I think it's NA actually. It's an NA value for every pixel outside the boundary, and every pixel inside the boundary has its own ID. So it's just like going from 1 to 6,000. I think we have 6,000 cells of this raster inside the boundary. So it's just basically coloring by ID, which doesn't really make too much sense because ID is just identifying the number of the pixel. But so just can see how this gray area outside is because it's NA, and that happened when we cropped this raster to the boundary file. Okay, so if you come down here to the next chunk, now we're basically going to start interpolation with this raster that's been cropped to the boundary of the field. So to do that, we're going to come to this next chunk, use that assign symbol, and then we're going to use the function gstat that comes from a package of the same name, actually. And it has, so the first argument here is formula. I just want to say formula equals, so, what we want to interpolate here is yield, right? So if we go back, you don't have to do this. I'm just gonna print here our yield object that was the yield 17C. The column that we want to interpolate here is, I'm selecting yield pounds per acre, right? So this is yield in pounds per acre, and it was already cleaned. So it would be yield pounds per acre. And the way that the formula works is you just say tilde, which is that wiggly line 1. This is how you would say that you want to interpolate this specific variable. And then also we need to tell this function, I'm adding a comma, hit tab just for visualization purposes. We need to tell it what's the data that we're going to use. So the data equals the yield 17 underscore C right there. So if you run this, nothing really shows after it. So if we just print that, it's not very intuitive, right? It's just showing like there's a variable 1 and just showing the formula, showing the dimensions of the data, but not much else. So if you get the class of this object, just so we check that, it is a gstat object and also a list object. So it is behind the scenes, we're basically defining what variable we want to interpolate, but the interpolation has not happened here in this chunk. We're just defining that structure at this point. So now if we come down to the next chunk.
I'm sorry, could I interrupt you for a minute? Because I'm not really sure about a couple of things, and I expect maybe one or two of our students are also a little bit unsure. Could you go back and explain exactly why we did the step before this, where we assigned 1 to 6,000 to our raster cells? What exactly were we doing there? I'm not sure I understood what we did. Yeah, there.
Yeah, so we started off creating a grid as a vector file, right?
Right, I understood that, yes.
And the thing is, the function that we're using next to do interpolation, it needs a grid in the raster format.
Right.
So if you give it a vector grid, it's not going to work.
Right.
And so we basically transform this grid that we're going to use for our interpolation into a raster, so it would be accepted, I guess, by the interpolation function. And then we also, whenever we did so now, so besides just transforming to a raster file, we also cropped the raster to the boundary. And so whenever we do the interpolation, it's not going to try to interpolate beyond the boundary of the field, because these values are NAs. It's only going to use
map showing us, though. It's just showing us the cells overlaying on the original map.
Yeah, yeah. So if you think of it here, we have 3 layers, right? So we have the yield data point behind it. We have the boundary, which is in that blue polygon, and then we have this raster on top. And the raster on top is just being colored. It's using that ID of the pixel, which is not very useful really, but it's just a default. So that's why we see like a gradient of blue, darker blue in the bottom, and lighter blue on top, just because it's seeing that ID as numerical and assigning a color gradient to it, which doesn't really make sense. But yeah, it is a raster, right? So now each cell is kind of like a pixel in an image, pretty much. Where
all this map does is just visualize the raster layer that we've created. We haven't assigned any values to it. It's just the raster layer.
That's right. Yep.
Okay.
Mm-hmm.
Thanks.
Yeah. Okay, so just coming back here.
Can I ask something quickly?
Yeah.
What would happen if we use 10 by 10 pixel size, right?
Yes. Mm-hmm.
What would happen if we use smaller one? And maybe at 1 pixel, there wouldn't be any vector assigned to that.
So if we decided to do smaller grid size, one thing that would happen is the resolution of our interpolation would be finer, right? So you would be able to see more details in your interpolated map. And there's always a balance there, right? Because in this case, our underlying yield layer is pretty dense. So we could go with a smaller grid size that would make sense. However, imagine that if this, instead of yield, if this was like a soil sampling data where we had points, like imagine having 10 points across this field scattered out, right? and you did a grid size even of 10, would be way too small for the resolution of the actual data behind it. You can still do it. The software is still going to produce an interpolated map for you, but how useful is that, right? Like if your points are 1 kilometer apart that you actually sampled and you're trying to interpolate to a grid of 1 meter size cell, it's not very, it's not going to be a good product interpolation. So it has to do with that. Also, the smaller the grid cell that you define, the more computation time is going to take. I mean, and this is really something that you guys can try on your own afterwards, is if we change the grid cell to 1 meter instead of 10, it would take a lot more time to interpolate, just because now it has, 1 order of magnitude more raster pixels to interpolate on. And also something else I think it's a great question is to think like, so at the end of the day, we want to interpolate this yield map to have a continuous values of yield within this border, and also to match this with other layers. So we're going to be using elevation data, some different soil information, perhaps remote sensing, and we're going to combine all those things together to make a zone in the end. And it's useful to think about in the sense of like, well, let's say if I come up with a zone that is so specific that would be the size of the cell, the minimum size of the zone would be 10 by 10 meters. Even then, it's probably like for a zone approach, it doesn't make sense in a zone approach, but I'm just trying to make you think of like, even 10 by 10 meters, is that a size that is manageable by the farmer? Like, like if you go from, like if I made a grid cell of like 1 kilometer, I mean, probably the farmer is going to have multiple passes within that cell. But if I do it with 1 meter, that's not even manageable from the minimum size of the equipment that they're going to be using, most likely. So there's always a balance of like selecting a size that makes sense from a management perspective as well. And that is not too fine that would take you days to interpolate just because you chose a very, very small grid cell size. Does that make sense?
Yeah, thank you.
Yeah. I mean, does that make sense? Like, was that, guys? Yeah, and this, I actually initially, I defined grid size to be 5 meters, and it was taking, I don't know, 6 minutes to do interpolation. And then I thought, 10 is good enough, and it's good enough to show the concept, and it's probably also a good enough management size. And, and this, again, it can be something that it can even change depending on the specific operation that you're working with. Like if they have an equipment of a certain swath, you can always use that as a grid size cell to really inform this. Okay, so if we come here on our next chunk, it's called the IDW pred. This is where we're going to basically match the formula we set up above with the actual raster file and predict then using those 2 layers. And this is where the prediction actually works. So
here we're actually starting to use the inverse distance weighted method, right?
Yeah. So I mean, we defined that, the method and the formula up here, but it has not been applied yet to the raster. That's what we're going to do next.
You want to take just a second, a minute, to describe to the students briefly what the inverse distance weighted method does, how it compares to simple averaging?
Yeah, sure. So what the inverse distance weighted method does is it looks for neighbors of a given grid. So in this case, right, so if we think about the grid set, well, let's look at this because it's easier to really see the cells, I guess. So if you think of like any cell here that doesn't have any data point, it's like blank at this point, and we actually want to interpolate over to have a continuous map. It's going to look at that cell that we want to interpolate over. It's going to look for neighboring actual data points that were collected around it, and it is an average weight pretty much. And the way that it's weighing that average is the closer the points are to that point that you're interpolating, the more weight they're going to have on that average. And the farther away the actual points are from the grid cell, the last weight they're going to have on the average. So it's basically saying that, the closer something is to where you want to know the value, the more correlation probably has to that actual value that you want to know that you didn't sample. So it's just using distance to give importance of how much a given point is affecting your interpolated point.
It's not just doing a linear interpolation either. It's looking all around.
Right.
So
Right.
it's not just the point that's like next to you on the right or on the left. You're looking at all the points around you and weighting them by distance. So it's used a lot by people who do spatial analyses.
Right. Absolutely. And this, again, is one of the simplest methods. There are more robust methods like kriging and different types of kriging that you guys are going to see with a different instructor. But this is very useful because it is very simple and still applicable. Okay, so if we come back here to our IDW pred chunk, we're going to use a function called predict. And the first thing that we're gonna give it is the IDW model that we define above. So the IDW underscore mod. And the second argument is the grid in the raster format. So grid underscore R. So this is what you should be seeing. And this is where it takes a little while because, it actually did, at least on my computer, didn't take that long. But I remember when I have a smaller grid size, it was taking a little longer to really do this. And this, again, this code right here is the one that is actually doing the interpolation. That's the step where that magic happens. And if we just, again, print it, we see that it is, again, a stars object. So it is a raster object. Yeah, just confirm that. And then, okay, all the magic happened there, but now let's actually plot this to really see our interpolated map. So here we're going to start from scratch, really. We're not going to use that previous map that we were using up until now. So we're going to start with the ggplot call. I'm not going to define any data or aesthetics at this level. I just want to leave everything blank, add a plus and hit tab. And we're going to use a geom underscore stars, which again stars is the package name for raster files. So this is what we're going to do. And we can just say data equals our IDW pred, so the predicted interpolation. If you just run at this point, this is what it looks like. So you can clearly see now a couple of different things. One, we do see that there's that pixelated effect to it. So that's one thing because this is a raster file. Also, we don't have any gaps anymore within the boundary. It's been all filled by the interpolation. So now, I mean, this is our product, but it doesn't really look great. So let's change a few things about it. If you want to add a plus and hit tab, let's first change the color gradient here. Let's do the scale underscore fill underscore viridities. First changing that scale to what we were using before, so it becomes easier for us to see. After that, I also want to add here the boundary, just so we see both of them together. To do that, we add a plus, hit tab, and now the boundary is vector. So to add a vector file to a ggplot, we use the geom underscore sf, which is what we've been using a lot up until now. And then we just say data equals boundary underscore w, add a comma. And I just want to say fill equals NA so we can see through it. It doesn't hide the pixels behind it. If we run at this point, okay, now this is looking more like what we were used to. So you see now, it's kind of interesting that the raster file itself did not set up, it was not seeing the coordinates as spatial, and it was like that distorted map. But when we bring in the boundary, it does like place things in the right place because for some reason, the vector file brings that information to ggplot already. So we see now that we do have, we do see the cells, which are, can think of them again as like pixels in a picture, right? They're all, and each one of these pixels have a value that represents that interpolated EO data. And just quickly here, I want to add another plus and tab. I just want to add now also the grid in the vector format, because that's the easiest for us to see. So we're going to use geom sf and then do data equals grid underscore v, because it's in the vector. If we show the, we could show the raster too, but the raster, as we've seen prior to this, is not very easy to see, like really the cells. And really the cell size is the same between vector and raster. So I just want to show you that. So if we just change the transparency, which we do by changing the alpha argument to 0.5, add a comma, I want to say fill equals NA, so we can see through it as well. And I just want to change the size of the lines of the grid to make it easier for us to see as well. So size equals 0.1. So this is what I would like you to do. If we run that, you can see now that grid overlaid on top of both the interpolated layer and the boundary. And so we can kind of see how it matches now. I mean, we can't here because it is not a interactive plot, but you can kind of see like how those pixels that we're seeing behind match with the pixels of the grid. That's pretty much what interpolation did. Also notice how all the gaps that we had before, again, this layer of eel we're seeing, it is the interpolated one. It's not the original one. So now on the interpolated one, you would not expect to have gaps. And we don't, right? You don't have to do this, you can stay where you are now. I just want to come up here and show you like all those gaps were filled, and not only filled, but also all the other cells were also recalculated based on its neighbor. So even the grid cells, the head points underneath them have changed.
Yeah, how much confidence can we have with the inverse distance weighted method when we're extrapolating, for example, between the edge, between the boundary and the buffer edge that we cut all those cells out from?
Yeah, that's a great question that I actually don't think that for that specific place, we don't have even a way to measure, right? Because we assume that those points were erroneous in the first place and remove them. And now the interpolation pretty much filled them back in, but we don't have points that we think were truthful to really check how different they are from the interpolated points, right? And this is a great point, because IDW natively does not give you a measure of certainty. We can always use some machine learning approaches to like remove some of the data points, run IDW with the remaining, which is going to fill everything. And then you compare the filled parts of that model with the points that you removed and see how different they are. That's one way that we could assess the quality of IDW overall. And there are different ways of like, defining how much data you use for modeling, how much data you use for testing. And it's a whole semester on its own, just that conversation and that process. But for places of the field where we do have data points, we could do a quality assessment of IDW. But for points that we removed because they were erroneous, we really don't have the good ground truth data to check for them.
The reason I bring this up is like in the future, if you're going to be using this map to make management decisions, for example, to decide on rates of something to apply, you really have to be very careful about these areas where the data are extrapolated, so we're really sort of reaching out rather than having data all around us and making a nice estimate of what might be in between. So you just need to be aware of that and be careful. And, one way to reduce your risk there would be to have some sense of how accurate the data that we clipped out are. I mean, we put in a pretty big buffer. We used what, 10 meters? Something like that. Was it?
Maybe it was 20.
20, yeah. So that's a pretty big buffer. That's, almost 70 feet. So we could reduce the size of the buffer, the width of the buffer. And so anyway, here, this is a learning exercise, but if you're applying this to real life, you really want to consider those parameters more carefully.
And that's a great point, because another option here would also to basically, instead of using the boundary as our limits, to use the negatively buffer boundary as the limits, right? So the interpolation will not even try to go all the way to the boundary. That's another option too.
One of the things that in this field that, we definitely have errors on the north and south ends from the machine, because that's the machine where the machine was turning in and out of the field. But the west and east boundaries, probably the original data were pretty accurate, almost right to the edge of the field, because the machine was running up and down, right? So if you've had a couple of rows that were harvested in 4-row mode, and the operator didn't say they were in 2-row mode, then obviously you can throw those out. But maybe the next pass in, the data were reliable. So you can make your own judgments about that in the future.
Yeah, and I mean it's really flexible, right? We can play with the size of the buffer. We can play with like the size of the grid that we're extrapolating. There are different components here that can be adjusted depending on the use and the data behind it.
You have the script now, so you just have to change one number and run it again, and there you go.
Exactly. Yep, that's exactly it. Okay, so our class goes till 10, is that right? Or 9:15?
10.
Okay, so let's do what I want to do now is basically, so the map, the interpolated map that we're seeing is raster, which is fine on itself, but for the reasons that I want to take you guys in the next exercises, I want this back to vector. I want this to be back on a polygon format, just because that's the file type that I decided to use as default. So for example, whenever we do this for elevation or for remote sensing, I'm always going to be extracting all those layers using the same grid in a way that at the end, when we do management zones, all layers match both in the resolution that they have, but also on the extent of those pixels. So we know that a pixel from let's say from satellite is matching the same place of the pixel that would be on the elevation with the same place as it would be for yield. So they're all matching throughout. And even though I was saying pixel just now, but I really want that to be tiny polygons back again. And that's basically what I mean by doing a grid extraction, is extracting those values back to a polygon shape, still in the same size of the grid cells, but just not raster anymore.
This is a really important step, because you have to try and match, the polygon size to your satellite images. Otherwise, you can't do a graded analysis. So this is a very important step here. Yeah,
that's definitely true. And also, I'm still seeing if we're going to be able to do the satellite imagery exercise and how that would work, as far as how much I want to involve you guys on gathering the data. But the satellite that we'll be using has a spatial resolution of 10 meters. So we would match, at least the spatial resolution would match with what we have on this grid. Okay, so to do that, to transform now our interpolated yield data back to a vector format, so it's tiny polygons rather than pixels, so we start off with this object IDW pred, which is the predicted IDW model that we have up here that we just plotted. Use a pipe, hit tab. We're going to use again this function called st_s_sf, which is basically used to transform objects that are not vectors into vectors. So now IDW pred is not a vector, is a raster, as we saw. We want to transform this into a vector, and we just have to change a couple arguments here. So the first one is s points equals false. Add a comma, hit tab, and the next argument is merge equals false. And finally, you don't have to run this yet. We have one more thing that I want to change here. I want to add a pipe and hit tab, and I just want to rename our variable has changed name, if you notice, from yield pounds per acre to var1.pred. That's the default of the IDW algorithm. I just want to change that back to something, instead of being calling var1pred throughout now, I just want to change that. So I want to use the function rename, and I want to call this IP let me think about why I was using, well, IP yield underscore pump breaker. And if I recall, if thinking of my past self when I decided this, I think the I is for interpolated, or maybe IP, maybe both IPs for interpolated. So I know that this is not the true yield data like point data is actually the interpolated version of that. And I have that information right on the name of the variable. So it'd say IP yield pump breaker equals var1.pred, because that's how it's being called after we interpolate it. So if we just do that, and now we print this, we see that we have that IP yield interpolated, and we have the different polygons here on this object. And if we just check the class of it, it is now back to an SF object, meaning it's a vector and it's also a data frame. Okay, let me see here. So we have just 2 more chunks here. I think, is it okay if we just go probably till 10:10? I mean, for you guys here in the room, do you have to run? Do you have a test afterwards? No? Okay. So is it okay with everybody on Zoom if we just go a little bit more just to finalize the 2 chunks here? Awesome.
Needs to go can leave, and we're of course recording this so you can catch up at the very, at home.
That's true. That's true. All right. So what I want to do next here is just to plot again the same object here that we created now, that is going to be slightly different than before, than the plot that we had above. So to do that, again, let's start with a ggplot, add a plus, hit tab. And because this now is vector, we use geom SF. So geom SF, we say data equals this object here. So idw pred v, add a comma, hit tab or enter. I keep saying tab. And I want to change some of the aesthetics. So we use that AES function, and I want to say color equals the name right there, the IP yield pump breaker. And again, adding a plus after the last parentheses, and just changing the color palette to scale underscore color varieties. Underscore varieties. And here is really where we can definitely see, because okay, let me just take a step back here and say, we had the yield vector point data. We created a grid that was initially vector, which was from the grid to raster. We interpolated the grid raster with the point yield data, and that created a raster of the interpolated yield map. Now we're transformed the raster to vector again. In this case, now it's not point anymore. As you can see, it's polygons. So now we have polygons of this yield interpolated data for this field. That's why you kind of see the pixel, even though they're not pixels anymore. Now they're tiny polygons with the same value as they had in that previous raster pixel format. And then this last code here, you can just go ahead and run it. I left the code for you, just so we can see now. So, okay, let me just say what's going on here. So if you look at the code, we're basically taking this vectorized interpolated yield data and just getting a geom density of the distribution of that interpolated yield data. So we see now this distribution here, that it definitely looks different from all the others that we've seen. It looks different from the yield raw data, looks different from the yield clean version, because now it's basically clean version interpolated, right? So it's a slightly different looking, but we just see how, I just wanted to show you that the distribution of the yield data now has slightly changed because it's been interpolated, and we have more data points after interpolating than we did before, because we're filling those points. Okay, so now the last thing I want to do, the last chunk I have for you, is exporting this. And this is very important because we're going to be saving this layer here to file, for the main reason that at some point we're going to need that again. So we're going to export now, and in the future when we need that again to do the zones, we're going to bring that back in instead of having to rerun everything again and having that object in our environment. So let's export this to file. To do that, because it is a vector file now, it's a polygon vector file, we're going to use the SF package to do that. And the SF package has a function called write_SF. And this is, just making a parallel. You see this in all programming languages, regardless of what file you're working with. Whenever you bring in a file, you always use something, read something. So read CSV, read SF, read something. And when you're writing to file, you're using the write version of that. Just to make that parallel quickly here. So the first thing that we give it is the name of the object that we want to save to file, which is that IDW_pred_v. And then if you add a comma, hit tab, hit enter, sorry, and open and close quotation marks. So now we're going to define the path where we want this to be saved and the name that we want to give it. So you open and close quotation marks, hit tab inside of there. You see that right now, the path that is showing us is inside of our code folder, right? We want to get outside of that to do that .. So now you should be seeing the directory at the root directory of your project. And then I want to go into data. So go into the data folder. We're going to create a new file that I want to call. So let's do this. If you just hit tab and you have less things than I have here, you can just select that KB2 yield 2017 clean.geojson that you should have, or something like that. Like this is the version that I created for this, the clean version that I created. Maybe you name differently. You're going to use that file, but we're not going to just use this like this because that would overwrite our file. We don't want that. I just wanted you to do this because this gives you the scaffold to actually don't have to write all the file name. But after that clean there, I want you to add an underscore and IP, basically meaning that now this is the interpolated version of this file. So again, we should be inside the data folder, or we get outside the code folder, go inside the data folder, and we create this file that I just added the IP at the end of its name to say that was the interpolated version. And again, we're saving it as a GeoJSON file. If we just run that, for me, it's giving me some errors because I already have this layer in that folder. So it's just telling me that I should not be doing that. But in your case, I want to ask you to come here on the Files tab, click on that R blue button, go in Data, and make sure that you have this file that you created in your data folder. We will need this in the future. You have to have this. So this pretty much wraps up the interpolation. So you guys have been exposed to how to do interpolation using IDW. We did that for one of the cleaned yield data files during this exercise. I will have a homework that is basically going to be asking for you to redo this for the other two. Should be even simpler than the previous assignment because now all the names match. You don't not going to have to be thinking too much about that from across different files. But again, the goal here is that we apply the same processing approach on the interpolation side to all three clean yield data files. And we're going to continue then the exercise next, looking at yield stability. So now we're going to have yield values for this field across 3 years. And I want to bring them the concept of yield stability, how that's important when you're creating zones, and can we even incorporate that into the zoning, into creating management zones itself. So that's everything I had today. Anyone has any questions?
Dr. Bastos, I had a question.
Yeah.
Yeah, so when we created our vector file from the raster one, we should be, I mean, I was expecting something to be some small polygons with the color in them. Over here, when you zoom it in, it looks like that there are this grid with the lines colored for what the values they have. Why is that?
That is true. So that's a great catch. And I didn't get into that discussion because it wasn't really the point, but it's really just how ggplot names things. So when you have like a polygon in that case, there are two aesthetics you can change. One is color, one is fill. So color would be the line around it, the color of the line, and fill would be what's inside. So to kind of overcome what you're saying, we could just come back here. I mean, you don't have to do this. I just want to show, but if you want to do it, welcome to. You just add a comma, it's still inside the AES function. You add a comma there and just say fill equals the same variable. You're gonna have to also add another scale here, because right now we're just changing the scale of the color. You're gonna have to add a scale fill varieties to also change that. And if you run that, then it's going to look back to what we saw when it was a raster, because now it's changing both the outline of the polygon and the fill of the polygon using that same variable, right? And again, color changes the outline, fill changes the inside in the case of polygons. Yeah.
Okay, thank you.
Yeah, you're welcome. Any other questions? All right, I think that was it. So again, I will follow up by email with some instructions for the next assignment. And we're not going to be using that probably, well, next week. George, do you want to talk about next week? Or do you have, I don't know if George is still there.
I think everyone is aware that next week is spring break, so we're not having any courses next week, any classes next week. So we will reconvene on Monday, the 14th. On Monday, the 14th, Dr. Yafit Cohen from the Israeli Agricultural Research Organization will start talking to us about thermal remote sensing. And because of her time restrictions, she's going to do it on 2 consecutive Mondays. So Monday we'll hear from her, and then Wednesday, Dr. Bastos will pick up. She has sent me a paper that she would like you to read before her lecture. So I'm going to forward that to you today or anyway, the next couple of days, and you can just read it. The paper has a lot of equations in it. I don't expect you to understand all the equations or learn how to use the equations, but to get the background of the complexity of the work she's doing, okay? So that's where we are with that.
Awesome, perfect. Yeah, and I will also follow up with instructions for this assignment. Again, it should be simple, especially as you've done something similar and even more complex previously. So this should be pretty straightforward. Just so we get all those 3 years interpolated and exported. All right. Sounds great. If you guys don't have any more questions, I think we can close here. Thanks for sticking around later today. Sorry that I extended, but I think it was worthwhile to just finish this and not leave it lingering for the next class.
Awesome. And everyone have a good weekend and a good spring break, and we'll catch up again on the 14th. Just so you know, also on the 14th, I am traveling on that day. I hope to be at my destination by the time class begins. But Dr. Cabrera knows to begin the course. So if I'm missing, don't worry. Dr. Cabrera will take care of it.
Oh, George, just hold on. Spen has a question here. Can you? Well, I don't know if you can hear him.
Yeah, you just repeat the question.
I have a question on the assignment that we were working on yesterday that's due next Sunday. Is there any way we can hang around a little bit after and figure out how to locate the files I need?
Could you hear him?
No, I could not.
Okay, so Spen was saying that he was having issues with the assignment that they were doing now, and he was just asking if he could speak with you like now via Zoom after we finish here.
Of course, yes.
Awesome. So I mean, I guess Spen, if you would like to connect on your computer, because then yeah, because that would make it easier. Awesome.